In this video, we will be doing one more example from the chapter of circles based on the concept of cyclic quadrilaterals. Okay, so we are given a quadrilateral ABCD in this example, and we have said that there are internal angle bisectors for the four angles of the quadrilateral. So we have the line AH is the internal angle bisector for angle A. The line BF is the internal angle bisector for angle B. Similarly, CF is the angle bisector for angle C, and DH is the internal angle bisector for angle D. Now, what we are asked to prove is that the internal angle bisectors of the four angles of this quadrilateral, they meet at some points E, F, G, and H, and that forms another quadrilateral. So EFGH is another quadrilateral formed by the intersection of the internal angle bisectors of the quadrilateral ABCD, and we are asked to prove that this quadrilateral EFGH, which is in the middle here, we are asked to prove that this quadrilateral is a cyclic quadrilateral. And we know from the definition of cyclic quadrilaterals, the property that must be satisfied is that the opposite pair of angles must add up to be 180 degrees. So if we can show that if any pair of opposite angles in this quadrilateral EFGH has a sum of 180 degrees, then we would have proved that the quadrilateral is a cyclic quadrilateral. Okay, so basically we are going to look at the angle FEH, which is this angle. Let me use a different color for that. Okay, so we have FEH, which is this angle here, and the angle FGH, which is this angle here, and we are going to show that these two angles add up to be 180 degrees. And once we do that, we would have proved that the quadrilateral EFGH formed by the intersection of the internal angle bisectors is a cyclic quadrilateral. Okay, so to do that, the first observation we make is that the angle FEH must be the same as the angle AEB, because these are vertically opposite angles. So angle FEH equals angle AEB. So angle FEH equals angle AEB, that is, they are vertically opposite angles. Okay, similarly, we can say that angle FGH is equal to angle CGD, because they are also vertically opposite angles. So angle FGH equals angle CGD, because they are also vertically opposite angles. Okay, now what is angle AEB and angle CGD? To find out what is angle AEB and angle CGD, we are going to look at the triangles AEB and the triangles CGD. So we have these two triangles here, AEB and triangle CGD. So from those triangles, we can find out what is angle AEB and what is angle CGH, and then we will substitute those values in FEH and FGH, and then we'll go on to show that the sum of FEH and FGH is 180 degrees. Okay, so let us now look at the triangle AEB and try to find out what is the angle AEB. Okay, so in triangle AEB, we know that the sum of all the angles inside a triangle is 180 degrees. So we will have angle AEB plus angle EAB plus angle EBA is 180 degrees. So from that, we have that the sum of the internal angles of a triangle is 180 degrees, and therefore we can write the angle AEB to be equal to 180 minus angle EAB, which is this angle here, and minus angle EBA, which is this angle here. Okay, so we get this expression over here. But what is angle EAB? This angle here, EAB, is half of the angle A, because AH is the bisector of angle A. So therefore, we can write this as 180 degrees minus half of angle A. And similarly, what is angle EBA? EBA is this angle over here, which is equal to half of the total angle B, because BF is a bisector of angle B. So therefore, we can write this as half of angle B. So now we can write this as 180 degrees minus half. If we take the minus half as a common factor, we can then have angle A plus angle B inside the bracket. So we have taken the minus half as a common factor outside the bracket. So we get angle AEB, which is this angle over here, to be equal to 180 minus half of angle A plus angle B. Okay, so similarly, we will do the same process for the triangle CGD and find out the angle CGD. So therefore, as before, we have in the triangle CGD, which is this triangle over here, we have the sum of the three angles of the triangle to be 180 degrees. And from that, we can find what is the angle CGD, which is this angle, that is equal to 180 minus the angle GCD minus the angle GDC. We have just moved these two to the other side of the equal sign. Okay, so now we have an expression for CGD, and like before, the angle GCD here, which is this angle, that is equal to half the total angle C, because CF is a bisector of angle C. And similarly, the angle GDC, which is this angle over here, is equal to half the total angle D, because DH is the bisector of angle D. So we can write angle CGD now as, so let us now call this result here as equation 1 and this result over here as equation 2. And from our previous discussion, we have angle FEH is equal to angle AEB. These are vertically opposite angles. And similarly, angle FGH is equal to angle CGD. Again, they are vertically opposite angles. So we will use that result now. And then we will use the equations 1 and 2 and add them together to show that the two angles FEH and FGH add up to be 180 degrees. And if they add up to be 180 degrees, then the quadrilateral EFGH is a cyclic quadrilateral. So we have from our previous discussion, we have angle FEH is equal to angle AEB, and this is equal to, from equation 1, this becomes equal to 180 minus half A plus B. So that is 180 degrees, or let me write that in the next line. That is equal to 180 degrees minus half angle A plus angle B. So we have angle FEH given by this expression. So this is our angle FEH. And similarly, we have the angle FGH. So angle FGH is equal to angle CGD. And angle CGD from our equation number 2 is 180 degrees minus half angle C plus D. So that gives us 180 degrees here, 180 degrees minus half angle C plus angle D. So we have these two expressions now. Now let's see, we have the expression for FEH and also for angle FGH. And now if we add these two, let's see what we get. If we add FEH and FGH, so angle FEH plus angle FGH is basically the sum of these two expressions. So that will be equal to, let me write that spread out further, so it's easier to write the entire expression in a single line. So angle FEH plus angle FGH. Okay, so that is equal to, first of all, angle FEH is given by this expression over here. So that is 180 degrees minus half angle A plus angle B. and then plus FGH. FGH is this expression over here. So we'll have plus 180 degrees minus half angle C plus angle D. Okay, now we'll just add up all the terms. We get 180 plus 180, which is 360. So that will be 360 degrees. We'll have minus half. So we can have the half as a common factor again. So if we take the half as a common factor, we'll have half into angle A plus angle B plus angle C plus angle D. Okay, now what is angle A plus B plus C plus D? That is the sum of all the angles in this quadrilateral ABCD, and we know that the sum of all the angles in the quadrilateral is equal to 360 degrees. So therefore we will get 360 degrees minus half into the sum of all the angles inside the quadrilateral, that is angle A plus angle B plus angle C plus angle D, is also 360 degrees. So we get 360 degrees minus half of 360 degrees is 180 degrees. So therefore that becomes equal to 180 degrees. So we now have the angle FEH plus the angle FGH. These are the pair of opposite angles in this quadrilateral EFGH, and we have shown that the sum of the pair of opposite angles in that quadrilateral is 180 degrees, and therefore we have the quadrilateral to be cyclic. Okay, so we can state now that since the sum of the opposite pair of angles is 180 degrees, therefore the quadrilateral EFGH is a cyclic quadrilateral. Okay, and why is that the case? Because sum of opposite pair of angles is equal to 180 degrees. Okay, so therefore we have proved now that the quadrilateral EFGH, which is formed by the angle bisectors of the bigger quadrilateral ABCD, is indeed a cyclic quadrilateral.